Okay, so in my absence today, I've prepared this short presentation which will cover the rest of the topic on projectile motion, which means next week we'll be stucking into our next topic, 1.2, which will be on uniform circular motion. Alright, but before we begin, just maybe a brief overview of what we covered in our last lesson. So we ended up having a look at air resistance and what we call the quadratic model of air resistance, which is the one that applies best for the kinds of speeds meters per second kinds of speeds you might occur in everyday life. So at these kinds of speeds, air resistance can be modeled using the equation that's shown on the right there. So air resistance is proportional to CD, the coefficient of drag, which if you remember is a number that describes how streamlined an object is. So a streamlined object like a bullet or a sports car will have a low coefficient of drag number, so maybe 0.3, 0.4, something like that. Whereas an object that's quite, flat or square, like, just a box or something, might have a larger coefficient of drag, maybe 1 to 2 or even higher than that possibly. So the larger the coefficient of drag, the less streamlined it is and the harder it is to move through the air. So it's proportional to coefficient of drag. It's also proportional to air density, which if you remember is basically how heavy the air is, which is defined as the mass of 1 cubic meter of air. So for example, air density at sea level is approximately 1.225 kilograms per cubic meter. In other words, a cubic meter of air at sea level will weigh 1.225 kilograms. As you go higher above the ground, the air gets thinner and therefore the air density goes down. Air density can also be affected by temperature. So hot air density tends to be less than the air density of colder air. And then the last one, well not the last one, but the next one is the cross-sectional area, which is the area of the front of the moving object. In other words, how much of the front of the object comes in contact with the air. And that's obviously measured because it's an area in meters squared. And then the last one, and probably the most important one at many speeds, is the actual speed of the object itself, v. So air resistance is proportional to the speed squared, which means, as with all quadratic relationships in physics, if you double the speed, you're going to quadruple the force. If you triple the speed, you get 9 times the force, and so on. So that means that air resistance will build up quickly with speed. So it becomes very important at higher speeds. So we looked at that. What we want to look at today is actually to look in a qualitative way, in other words, a descriptive way, at how the path or the trajectory that the projectile takes through the air is affected where we actually do include air resistance in our figuring. So to repeat what we said last time, air resistance always acts in the opposite direction to a projectile's velocity at any point in its motion. So at any point in its motion, whichever way it's moving at that second in time, the air resistance will always be in the opposite direction. And that means it's going to affect both the horizontal and the vertical velocity components for that object. And that's a little bit different to what we've seen previously. When we were looking at projectile motion without air resistance, we saw that the vertical velocity changes because of acceleration due to gravity acting on it in the vertical direction. But the horizontal velocity component always remained constant throughout the motion. That won't be the case here. What we'll see instead is that the horizontal velocity component will decrease over time. So we can kind of see it summarized in these two graphs on the side here. For these two graphs, the blue line represents what would happen in the absence of air resistance, and the red line is an indication of what would happen if we did include air resistance. So we'll start with the top one. The top one represents the velocity, vertical velocity. So we'll see the blue line represents what would happen to the vertical velocity in the absence of air resistance. Now this would be a unilevel projection we're looking at here. And what you'll notice is that blue line, it goes downwards with a constant slope. It's a straight line downwards. And that's showing us that the vertical velocity decreases over time because gravity acts downwards on it. For the first part of the motion, the vertical velocity is positive, which means that would be the upwards part of the motion. But it decreases until it reaches 0 here. So that would represent when you're at the apogee. So at the apogee for a split second, your vertical velocity is 0. And then it becomes negative, which would be the downwards part of the object's motion. So on the downwards part, the velocity is negative. And if you found the slope of that graph, as you might remember from last year, the slope of a velocity time graph is equal to the acceleration. So we'd expect the slope of that graph would be equal to negative 9.8 meters per second squared. In other words, acceleration due to gravity. So that's vertical velocity without air resistance. With air resistance is represented in red here. And we can see that the overall effect is on the way up, it decreases faster. The vertical velocity decreases faster. And that's because on the way up, the vertical velocity component will be in the upwards direction, which means the air resistance will act downwards on it. So basically, you've now got two downwards forces acting on the projectile on the way up. You've got acceleration due to gravity, which is downwards, and you've also got the air resistance component, which is also downwards as well. So those two downwards forces will act together to give a larger downwards force than what you would have normally. So the overall effect is the downwards acceleration is larger than it would be in the absence of air resistance, which means it slows quicker. So you can see that with air resistance, the projectile slows to zero sooner. So it slows to zero at this point in time rather than later on without air resistance. So it reaches its apogee sooner. But then on the way back down, it gets a little bit more complicated. You can see on the way back down that the slope of the line with air resistance is less than without. And that's because on the way down, acceleration due to gravity will be acting downwards on the falling projectile, but the air resistance will be acting upwards on it. So we've got two opposite forces. They're not equal and opposite, so they don't cancel exactly, but what they will add up to is a reduced acceleration downwards. So, in the absence of air resistance, acceleration due to gravity might be 9.8 meters per second squared downwards. But with air resistance, it might be something like 8 meters per second squared downwards. So it's less. It still falls downwards and it still speeds up as it falls, but it won't speed up as quickly because of that reduced downwards acceleration. And you can see after a certain point in time, the vertical velocity is actually less with air resistance as it falls. We'll get to that in a second, but that's important. So that's the effect of air resistance on the vertical velocity. The air resistance effect on horizontal velocity is much easier. So in the absence of air resistance, you just get a flat horizontal line, which represents the fact that the horizontal velocity component in the absence of air resistance remains constant. However, if you do include air resistance, which is the red line here, the horizontal velocity component will be reduced for every second that the projectile is in the air. So it'll get smaller and smaller and smaller and smaller and smaller. It never quite reaches zero, but it'll get smaller and smaller and smaller over time. So that's the overall effect on each component. What then does it add up to as a whole? What's the complete effect on the trajectory? Well, the complete effect on the trajectory looks a little bit like this. I will mention here that the overall effect depends on whether you're talking about unilevel, bilevel, or horizontal projection examples. On this first slide here, we've got sort of an example for unilevel. So for unilevel, you can see in blue that if we get rid of air resistance, it's a symmetrical parabola, right? If we include air resistance, then the overall effect will be that the apogee will be reached sooner, so in other words, in less time. The apogee will occur at a lower height, and the apogee will occur at a closer horizontal distance to the launch point. We can kind of see that here. So the apogee is closer to the ground vertically than it was without air resistance, and it's also closer horizontally to the launch point than it was without air resistance as well. So the apogee is lower, closer horizontally to the launch point, and it occurs in less time. You'll also notice another fact there, which is that the trajectory is no longer quite symmetrical. So before, if you put a line down the middle for unilevel projection, the two sides of that trajectory would be mirror images. It's symmetrical, in other words. Here though, if you put a line down the middle, you can see that it's kind of steeper on that side. It's no longer symmetrical, and it's steeper on this side because the horizontal velocity is much smaller. Air resistance has been acting on the horizontal velocity and reducing it, so by the time it gets to this point, it's barely moving horizontally at all. It's mainly just falling out of the air. So that makes it much steeper on this side of the apogee. So it's no longer symmetrical, so we can no longer call it parabolic motion. So that's for unilevel projection. Now the time of flight, the overall effect of the time of flight on a projectile's motion depends on what kind of situation we're talking about. With unilevel, it's a bit complicated because with unilevel projection, there's two parts to it, right? There's the upwards part as it's going up towards the apogee, and then there's the downwards part as it falls from there. On the upwards part, gravity will be acting down on the projectile, and air resistance will be acting down on the projectile as well. That is if we consider the vertical velocity component. So that means there'll be a larger downwards acceleration acting on it, and it will reach the apogee in less time. On the way back down, however, acceleration due to gravity is still downwards, but the vertical part of the air resistance force will be upwards on it. So that leads to a reduced overall acceleration in the vertical direction, which means it actually falls slower than it would otherwise. So it slows down faster on the way up than on the way down, and actually takes slightly more time to reach the ground than it would if we just dropped it from that height without air resistance. So it's a little bit less time on the way up, but more time on the way down. The overall effect, though, is that the time of flight is reduced. Because even though it might fall slower than it would without air resistance from this apogee here, without air resistance it's actually falling from a higher height. You can see it's falling from a much higher height without air resistance than with. So you can show, the maths is complicated and we won't be doing in year 12, but you can show that for a uni-level case, the overall time of flight is reduced with air resistance compared to without. Okay, so that's uni-level. If we were to move on to horizontal projection like we have here, in that case, we can definitely say that the time of flight will be increased, because for horizontal projection, the entire trajectory is downwards, right? It just falls down, but it's falling sideways as it does that. That means as it falls downwards, acceleration due to gravity acts downwards on the projectile, but the force of air resistance, or at least the vertical part of the air resistance force, will be acting upwards on it. So there's two opposite forces acting on it, which results in a reduced overall force acting downwards on it and reduced overall acceleration in the vertical direction. So that means it falls slower than it would without air resistance, which means it has a longer time of flight, a slightly longer time of flight for horizontal projection. For bi-level, it's a bit more complicated again. For bi-level, it's all about how much of the trajectory is up and how much of the trajectory is down. So if we look at a bi-level example here, where your launch height is higher than your landing height, and if we go around the apogee, we can see that more of the trajectory is on the downwards path than the upwards path. We know that the time to reach the apogee is reduced with air resistance on the upwards path, but then the time to fall from the apogee down to the ground is increased because of the way air resistance acts. So what that's going to mean in most cases is, because you've got more downwards motion than upwards motion, that'll generally lead to an increased time of flight for bi-level projection if you're launching higher than your landing. If you flip it around and you had a landing height that was above your launch height, so launch from here, land up here, we would probably expect a reduced time of flight. Okay, so increased time of flight if you're launching from a higher height, decreased time of flight if you're launching from a lower height. Okay, again, the mathematics we're not going to show here, so we just basically just memorize this, okay, and hopefully it makes sense. Okay, so that's kind of our effect on trajectories if we include air resistance. The very last part of this we look at is on terminal velocity. So we've talked a bit about terminal velocity already in the previous lesson. The terminal velocity for an accelerating object is the maximum possible speed it can reach, beyond which the acceleration disappears and you can't go any faster. So what happens there is you'll always have, for a moving object with air resistance, you'll always have two sets of forces acting on it. You'll have the force that acts to push it forwards, what we call the accelerating force, and then you'll have, acting in the opposite direction, you'll have air resistance, and depending on the scenario, you may also have friction as well. When the force acting forwards on it is equal and opposite to the resistive forces acting in the opposite direction, then the overall net force will be zero, and if the overall net force is zero, then by Newton's second law, that means the acceleration is zero as well. Acceleration of zero means the object will continue to move at that speed, but won't accelerate any faster. So in other words, it won't move any faster than that. So that's the maximum possible speed that object can reach. So the first example we'll look at here, shown in this wonderful diagram on the right, is the top speed of a car. So So top speed of a car moving along a flat stretch of road. That top speed is dependent on three forces that act on the car. There's the force from the engine that pushes on the wheels and pushes the car forward. And then acting in the opposite direction, there's air resistance, which will be dependent on the car's speed. And there's friction as well, which to a large degree is also dependent on the car's speed. There's actually two bits that make up friction. There's friction within the moving parts inside the engine itself, but there's also friction between the car's tyres and the road. At high speeds, the friction between the car's tyres and the road are probably more significant. But actually at high speeds, the largest force overall is the air resistance. Friction's still important, but air resistance is more significant because we saw earlier that air resistance is proportional to the speed squared. So at high speeds, it gets much larger. So what will happen here is as you go faster and faster, the engine force will remain the same, but the air resistance and friction forces will increase with speed. Eventually, you'll reach a speed where the sum of the air resistance and friction forces acting backwards on the car will be equal but opposite to the engine force acting forwards on the car, giving you a net force of 0, and that will be the top speed of that car. So I think I mentioned previously, when I was young and stupid, I worked out that the top speed of the car I had at that point was 183 kilometers per hour. So at that speed, the engine force acting through the wheels and pushing the car forward was equal and opposite to the air resistance and friction acting backwards on the car, giving me a net force of 0 and a net acceleration of 0 at that speed, which means the car would continue to move at that speed no matter how hard I pressed on the accelerator, and it would never go any faster than that. That was its top speed, or in other words, that was its terminal velocity. So for a car, what you can do if you want to increase the terminal velocity is one of a few things. You can just put a bigger engine in it. Bigger engine will produce more force, and therefore you'll have to be going faster to cancel out that increased force. Or probably a smarter way of doing it is to make the car like more compact, so closer to the ground, more compact, and more streamlined. So reduce its cross-sectional area and reduce its coefficient of drag. Modern sports cars like Ferraris tend to do both. They stick a very big, very powerful engine in the car to give it more engine force, pushing it forwards. But they also streamline the body of the car and put it close to the ground as well to try to reduce air resistance. By doing that, the top sports cars can get the terminal velocity of it up to about 400 kilometers per hour just by doing that. Alright, so that's one example. A more common example would be a falling object, an object falling through the air. Now, when you have an object falling through the air, you'll have two forces acting on it. You'll have the force of gravity acting on it downwards, and then you'll have the air resistance force acting in the opposite direction, acting upwards on it. Now, the force of gravity acting downwards will be constant, right? We know from last year that the force of gravity is given by F equals mg. So the mass of the object multiplied by acceleration due to gravity, so in other words, multiplied by 9.8. So the force of gravity is constant, doesn't change. However, the air resistance force will change because, as we've said it before, the force of air resistance is proportional to the speed squared. So as the object accelerates and gains speed, its air resistance force will get larger as well. And that's kind of represented in this diagram on the right. We've got some guy jumping out of a helicopter. Hopefully he's got a parachute. At the beginning, when he's just jumped out, his downwards velocity will be 0. So it's no air resistance force. At the split second he's jumped out, and a downwards force of gravity of 833 newtons. That's for his particular weight, his particular mass. If we change the mass, we change the force of gravity. And then we can see, this is like snapshots in time. Start, a little bit later again, a bit later again. As he speeds up, his force of air resistance will increase. So it's 350 newtons in the next snapshot, then 700, then 833. And we can see that the air resistance force is getting larger. In the first two things here, the force of gravity is still larger, so they don't quite cancel. So there's still an overall net force acting downwards, so he'll still continue to accelerate and speed up. But once we get to this point here, the force of gravity downwards is 833. The force of gravity upwards is 833. Those two forces are equal and opposite, therefore they'll cancel. Net force of 0, so the skydiver here will continue to fall at that speed, but they won't go any faster until something happens, until they either deploy a parachute or they hit the ground. But other than that, they'll just continue to fall at the same speed forever, basically. So that's a common example. So how do we actually calculate acceleration due to gravity? How do we calculate terminal velocity? Well, we've got a little derivation we can do here for a falling object, and it's pretty simple. We just say that terminal velocity occurs when the force of gravity, Fg, is equal in magnitude to the force of air resistance, but opposite in direction. So Fg equals F air, in other words, the force of air resistance. Force of gravity is mg. Using our quadratic model of air resistance, force of air resistance is a half CD rho A V squared. And I've changed the V squared here slightly, and I've put a little, what looks like a T down the bottom as a subscript. It's actually a tau, it's one of those Greek letters. So V tau is usually used to represent terminal velocities, because in this case here, when we solve for V, we'll get the terminal velocity. So solving for V here, or V tau rather, the terminal velocity, you can show, I've left the algebra out here, but you can show that V tau is equal to the square root of 2mg over CD rho A. So that'll give the terminal velocity of a falling object if we know its mass, its coefficient of drag, the air density, and its cross-sectional area. Okay, so a couple of things to note about, well, one thing to note about this formula. You'll notice here that the force of air resistance is not dependent on the mass. So two objects with the same coefficient of drag, moving through the same air density and with the same area and the same speed, will experience the same force of air resistance regardless of their mass. So if you had a cork ball and a cannonball of the same size and the same everything else, even though they have vastly different masses, they'll experience the same air resistance force. However, the terminal velocity, even though the force of air resistance is not dependent on mass, the terminal velocity is dependent on mass. We can see that m appears in that formula. So if we dropped the cork ball and the cannonball from the same height, and they had the same characteristics, they would experience the same force of air resistance, but because the cork ball would be lighter, it would be more affected by air resistance, and therefore it would experience a lower terminal velocity. It would reach its terminal velocity sooner. Okay, so when you're talking about terminal velocity, mass matters. All right, so before we finish, just a quick example, a commonly used example of terminal velocity, and that would be skydiving. So the idea of skydiving is jump out of a plane or something like that from a high height. Fall, as you fall, you accelerate, and as you fall, the force of air resistance increases until eventually you reach terminal velocity. The force of air resistance upwards on you is equal opposite to the force of gravity downwards, and you'll continue to fall at that speed until you reach a safety height, at which point you deploy a parachute, and that slows you to a kind of speed where you can actually land safely on the ground. Now, the actual terminal velocity the skydiver reaches depends on how they position themselves in the air. So if you're just some guy that's never done it before and you're doing a skydive with like strapped to your guide or whatever, you're going to do something like this, the belly down posture, right? Where you kind of spread yourself out as much as you can. So by spreading yourself out like that, you increase two things. You increase your cross-sectional area, so you're presenting a larger area to the air as you fall, and you also increase your coefficient of drag as well, because you've got more drag when you do that. Now, the calculations are a little bit tricky because there's A, your terminal velocity will depend on the mass of the skydiver, but B, obviously the air will be thinner up the top where you jump out of the plane compared to when you're down to the ground. So your air density actually changes as you fall too. But the average sort of terminal velocity for someone in this position is about 200 kilometers per hour. So they'll fall about 200 kilometers per hour until they reach a particular height and then deploy a parachute. And then I think they slow down to something like 20 Ks, 10 to 20 Ks, and that's the actual speed they land at. If you tried to land, obviously, at 200 Ks an hour, you're just going to break your legs. So while they're falling, though, they're falling with a terminal velocity of about 200 Ks per hour. On the other hand, if you're like an extreme skydiver, you might do this, and you just kind of like put your head down and fall like that. Now, obviously, by doing that, you're reducing your cross-sectional area because you're just going head down, and you're also more streamlined like that as well. So reducing cross-sectional area and reducing your coefficient of drag will result in a much higher terminal velocity. So for head down, you're looking at more like 290 kilometers per hour for a skydiver. Okay, so I just thought I'd mention that. It's a commonly used example of terminal velocity, and one that we will see, you will see in your workbook and in your textbook. All right, so that's me done. Now you'll have some exercises to complete for this relief lesson. Make sure you attempt them before we come back on Friday. Okay? Thanks for your time.